What's up, everybody, and welcome back to OpenStax Algebra and Trigonometry, Chapter 2, Section 4, Complex Numbers. Let's do it. So explain how to add complex numbers. So first, what is a complex number? That's the broadest category of numbers that we have. So technically, everything is going to be a complex number, but what they mean here is the real component and the imaginary component. So for example, if you'd have a complex number as 5 plus 2i, that's in the format of a plus bi. So if I had another complex number, and again, we'll get to imaginary numbers more so later in this section, but I is simply equal to the square root of -1, which we can't evaluate with real numbers. There's no number times itself that's a real number that will equal -1. So we have 5 plus 2i, -3 plus 7i. So if I were to add these, I would add the real parts, 5 and -3, which is 2, 2i and 7i, which is 9i. That's how you do it. Done. So a very simple example to show that the product of two imaginary numbers is not always imaginary is as follows. If I do 2i times 3i, the real parts will multiply to give us 6, and the imaginary parts will give us I squared. So again, if we recognize that I is the square root of -1, if I were to square this, right, square I squared, it would get rid of the square root. Therefore, I squared is -1. Therefore, we can replace I squared with -1, which means this would give a result of -6, which is real. Boom, done. Here we're going to plug and chug, and we're going to solve for y when x equals 2i. So we've got 2i squared plus 2i minus 4. So 2i squared becomes 4i squared plus 2i minus 4. Once again, I squared is -1, so that's -1 times 4, which is -4 plus 2i minus 4. We combine like terms. -4 make -8 plus 2i is the winner for y. Done. Here we're going to plug 2 plus I in for x, so we've got 2 plus I squared plus 3 times 2 plus I plus 5. Okay, first I'm going to FOIL this, so that's going to be 2 plus I times 2 plus I. That's how we square a binomial. This one we're going to distribute that 3, which is going to be 3 times 2 is 6 plus 3i plus 5. And now let's simplify this. So first we got 2 times 2, which is 4. Then we've got a 2i and a 2i as they're multiplying. So 2i plus 2i is 4i. And then we got I times I, which is I squared. Again, I squared is just -1. So I'm going to take a little shortcut there. And then we've got this whole section. Now we can combine like terms. We've got 4 and -1 and 6 and 5. So that's 3, 9 plus 5 is 14, putting the real part first. And then 4i and 3i makes 7i for the win. Done. We're going to plug in 5i for x. So we got 5i plus 1 over 2 minus 5i. Now this is in and of itself fine, but the general idea is when we got complex numbers, we don't want to have an imaginary in the denominator. As such, we're going to multiply by something called the conjugate, both on the top and bottom. So it's the same as 2 minus 5i, except we flip the minus to a plus. And then we have to do the same thing on top because that makes it so that we're multiplying technically by 1, which is allowed. So now we're going to do our foiling. So we've got 5i times 2, which is 10i plus 25i squared. Again, the I squared is -1, so it's minus 25. And then plus 1 times 2, which is 2, plus 1 times 5i, which is 5i. We'll combine like terms in a second. Then on the denominator, we've got 2 times 2, which is 4. Then we've got 10i and -10i when they multiply. So I'm not writing it out because this is the beautiful part about the difference, or it's a difference of squares, but it's multiplying by the conjugate. The 10i and the -10i, those are going to cancel out, and that's how we get rid of the I on the denominator. Actually, I will write it out. Why not? Because it's the first example. So 10i minus 10i, but those will cancel. And then I've got -5i times 5i. That's -25i squared. But again, I squared is -1, so that cancels out with the minus. So on the bottom, it becomes 4 plus 25. So now let's combine like terms and finish this. So I got 10i and 5i, that makes 15i, -25 and 2 make -23, over 4 plus 25, which is 29. Last but not least, we're going to put this into a plus bi format. So it's going to be the real part first. So I'm going to split it up as negative 23 over 29 plus 15i over 29 for the win. Done. For the following exercises, plot the complex numbers on the complex plane. So you might be like, well, how do I do that? But it's really not so bad. The real number, aka this part, is going to go on the x-axis, or the real number axis in this case. And then this complex part, the negative 2i, is going to go up here. So we can just kind of number it out like this. We say 1, 2, 3, just a couple numbers. And then here we can say -1, -2, -3. Again, so -2 would represent -2i. So this would be 1 on the real number axis, -2 on the imaginary number axis. So there's the point. Done. So in this case, we've just got an I that we need to plot. Now, technically, that means the real number part is 0. So we're not going left or right at all on the real axis. But we are going up because that's a 1i. So we're going right here for the win. Done. Here, we're simply going to simplify. And the best way to think about this is to just treat I like a variable like x. And since we got plus between these guys, the parentheses aren't doing anything. So I'm going to rewrite it like so. And then I'm going to combine the 3 with the 5 and the 2i with the -3i. So we have 8 minus 1i, right? Because 2 and -3 is -1. So I'll just say 8 minus i. Boom. Done. Here we have a minus. And so I got to first distribute that minus. So I got -5 plus 3i minus 6. And then minus and minus makes plus I. Now I'm going to combine like terms. -5 and -6 makes a -11. 3i and I makes a 4i. -11 plus 4i. Boom. Done. Here we're going to start by distributing the negative. And I got -4 plus 4i plus 6. Right? Negatives cancel out. And then minus 9i. And then we're going to combine like terms. -4 and 6 make 2. 4i and -9i make -5i for the win. Done. Here we're going to distribute. So 3i times 5 is 15i. And then minus 3 times 2 is 6. And then I times I is I squared. So again, I squared is just -1. So if I replace I squared with -1, it's going to cancel out with that minus. So I've got 15i plus 6. And then to write it in a plus bi form, it would just be 6 plus 15i. Done. Again, we're going to distribute the 8 like so. 8 times -2 is -16. 8 times 4 is 32. So you notice it's 32i. Just like if it was 4x, it'd be 32x. So this is the final answer. Done. Here we're going to do some foiling. So first, -1 times -2 is 2. Then we do the outer. -1 times 3i is -3i. Then we do that, which is -4i. And then we got the last 2i times 3i, which is 6i squared. So again, these guys combine, -3i and -4i make -7i. Remember, I squared is -1, so that's really just a -6, or 6 times -1. So 2 and -6 combine to become -4 for the win. Done. Once again, we're going to FOIL here. 3 times 3 is 9. 3 times -4i is -12i. 4i times 3 is +12i. And 4i times -4i is -16i squared. Now, notice the -12i and +12i, they're opposite, so they cancel out. And then that's a -16i squared, or -16 times -1. That's what I squared is. So this just becomes a +16. And then 9 plus 16 is 25. Boom. So here all we're doing is we're simplifying. We're dividing this entire expression by 3. So I can break it up as 6 divided by 3, which is 2. And then 2 divided by 3, which is 2/3 I. And there we are in the format of A plus BI. So this is the winner. Done. Here we're going to divide both terms by I. So I've got 6 over I plus 4i over I just becomes 4. So now we've got this problem. We've got the imaginary number in the denominator. The way I'm going to get rid of that is I'm going to multiply it by I over I, right? So I times I is, of course, I squared. So I've got 6i over I squared plus 4. But I squared is the same as -1. So 6i divided by -1 is -6i, or -6i. Then I'm going to place the 4 in front because, again, we put the real part in front. There's the winner. Done. Again, we need to get rid of this denominator having an imaginary. So we're going to use the conjugate. So check it out. Here's the complex conjugate. Instead of 2 minus I, we're going to multiply by 2 plus I. So on top, we're going to do 3 times 2, which is 6. Then 3 times I, which is 3I. Then 4I times 2, which is 8I. And then 4I times I, which is 4I squared. And then on the bottom, we've got 2 times 2, which is 4. And again, with this complex conjugate, the nice thing is that you're going to get a 2I and a negative 2I, which means the imaginaries are going to cancel out. And then we got negative I times I, which is negative I squared. Again, since I squared is negative 1, negative I squared is negative negative 1, or 1 plus 1. Okay, now let's simplify. So we've got like terms here. That's 11I. So we're going to put, let's put it here, 11I. And then 4I squared, that's 4 times negative 1. So that's a negative 4 right here. 6 and negative 4 make a 2. And that's over 4 plus 1, which is 5. Last but not least, to put it into A plus BI form, it would be 2/5, right? 2 divided by 5 plus 11/5 times I. Done. Here we're going to simplify as much as possible. So first I'm going to rewrite negative 9 as negative 1 times 9. I'm going to do the same with 16. So the reason why I'm doing this is because now I can take the square root of negative 1, which is I. So I got I square root of 9 plus 3I, right? Square root of negative 1 times, or 3I times the square root of 16. Then what is the square root of 9? It's 3. And what is the square root of 16? That's 4. So remember, when the 4 comes out, it multiplies that 3 in front, so it becomes 12I. And then 3I plus 12I is 15I. Done. All right, here I'm going to break it up. I'm going to first make it 2 over 2 plus square root of negative 12 over 2. So 2 over 2 is, of course, 1. And then for the 12, or negative 12 on top, I'm going to break it up like so. I'm going to make it negative 1 times 4 times 3. I could also have broken it up and make it negative 1 times 2 times 2 times 3. But I did it this way in particular because I already know that 4 is a perfect square. So check this out. The square root of negative 1 is I. The square root of 4 is 2. And that 3 is stuck inside. We can't do anything to simplify that. And that's over 2. So 1 plus this. Last but not least, I can cross off the 2's on the top and the bottom. So my final simplified expression is 1 plus I root 3, boom, done. So when we get really big values of I, like I to the 8th or I to the 20th or whatever, there is a pattern. The I values repeat every 4th. So for example, I equals just your regular square root of negative 1, which is just I. I squared is negative 1, right? We already talked about that. I cubed is that negative 1, right? I squared times another I, so it'd be negative I. And then I to the 4th is basically a negative I times another I, which would be negative I squared. Since I squared is negative 1, it would come to positive 1. And then I to the 5th repeats because we're now just taking a 1 and multiplying it by another I. So if we carry out this pattern, we see that I to the 8th equals 1, boom, done. So as I mentioned in question 39, these imaginary numbers, when they're raised to exponents, they follow a certain pattern. So I to the 1st is 1, I squared is negative 1, I cubed is negative I. Oops, let me put it, make sure that it looks like an I. And then I to the 4th equals 1. So to figure out like a big number, like 22 is actually not that hard, but imagine if it was 222, that'd be difficult. So what you do is you take that exponent and you divide it by 4. So 4 goes into 25 times, but that doesn't matter. What matters is the remainder, okay? Now, if there was no remainder, it would be 1. If there was a remainder of 1, it would be I. If there was a remainder of 3, it would be negative I, but we got a remainder of 2. So that means that I to the 22nd equals negative 1. Evaluate 1 minus I to the k power for k equals 2, 6, and 10. Predict the value of k equals 14. So we're going to use this little binomial expansion calculator that I found, and we're going to give it a shot. And by the way, this is the technology portion where they want you to use a calculator. That's why I'm using one. So 1 minus I squared is I squared minus 2I plus 1. I squared, since that's negative 1, it's just going to cancel out with the 1, but let's write it out. So these guys will cancel, and we get negative 2I. That's for k equals 2. Now for k equals 6. So I'm going to take that and I'm going to throw it up on the whiteboard and copy it down, and then we'll simplify it. Check it out. So I to the 6th is, again, using our pattern, right? I to the 4th would be 1. I to the 5th will be I. I to the 6th would be negative 1. And then I to the 5th is just I, so that's minus 6I. I to the 4th is 1, so that's just plus 15. I cubed is just negative I, so that's plus 20I. I squared is just negative 1, and that's minus 6I plus 1. So we'll combine all the like terms. So we got negative 1, that's 14, that's plus negative 15 is negative 1, and then that is 1. So there's no, these guys all just cancel out, it looks like. And then we got negative 6I, that's negative 12I plus 20I, which is 8I. Now let's do k equals 10. So I'm going to take this, we'll put it up, and then we'll knock it out. So my guess is that there's a pattern here where the real number part is going to cancel out again, but we'll see if that's true. So I to the 10th, that's 4, and then an I squared, which is just negative 1, right? I to the 10th is negative 1. I to the 9th then is probably just, it's just I, so that's minus 10I. I to the 8th is just 1, so it's plus 45. I to the 7th is negative I, so then that's plus 120I. I to the 6th is like I squared, so then it's like minus 210. I to the 5th is like I, so that's minus 252I. I to the 4th is just 1. I to the 3rd is negative I, so that's plus 120I. I squared is negative 1, negative 45, minus 10I, and then it's plus 1. So once again, the 1s cancel, the 45s cancel, the 2 10s cancel, positive and negative. So it's true, we're down to just I values. So we got negative 10I, that's plus 120 is 110I. That's negative 142I. And then that's negative 152I plus 120, negative 152, that's negative 32I. So the pattern I'm seeing here, it seems like when this goes up by 4, we're multiplying this value by negative 4, because then we get positive 8I. Then we go up by 4, we multiply by negative 4, we get negative 32I. So I believe that the pattern would be for k equals 14. We multiply this by negative 4, which would give a value of positive 128I. Boom, done. Show that a solution of x to the 6 plus 1 is this. Well, basically what that would mean is if we plugged this in for x, we should get negative 1, because negative 1 plus 1 is 0. So again, I'm using my binomial expansion calculator, the technology that they said we can use to get my binomial expansion, where x is simply the I value. So now let's go ahead and replace all these x's with i's. And since the least common denominator is 64, I'm going to simultaneously convert everything to a denominator of 64. So I to the 6 is like I squared, so that's negative 1. So we got negative 1 over 64 plus, that's really, I'm going to make that 64, so that'd be 6 rad 3. And x to the 5th is I to the 5th, which is just I. So I'm going to make it 6I rad 3 over 64, right? Just doubling the top and bottom. Then x to the 4th is just 1, so that's plus 45 over 64, plus, that's only out of 16, so I'd multiply that by 4 to get 64, so that's 4 times 15 is 60. I cubed is negative I, so I'm actually going to change this to a minus. So we've got minus 60I root 3 over 64. And then that's minus 135, because I squared is negative 1 over 64. And then that's just I. And since it's out of 32, I'm going to double it. So that's plus 54I rad 3 over 64. And then I'm going to leave that 27 over 64. So for this to work out, this all needs to evaluate to -1. So my assumption is all the i's are going to cancel out. Let's see. So 6i root 3, 54i root 3 makes 60i root 3, and we got a negative 60i root 3, so those indeed cancel out like so. And then we got to combine these. Hopefully, again, this will equal to -1. So -1 plus 45 is 44 over 64. -135 plus 27 is, let's see, 1, take away 20, that's 115, -108 over 64, so minus 108 over 64. And then -108 plus 44, taking 44 away, basically that's 104, that's 64. Boom, which equals -64 over 64, which does equal -1, so we've proved our point. Done. Here we are going to simplify by just getting rid of the i's in the denominators. So for the first one, I'm going to multiply by I and I. For the second one, I'm going to also multiply by I over I, because I times I to the third is I to the fourth, which evaluates to 1. So check this out. This becomes I over I squared plus 4I over I to the fourth. I squared is -1, so that's just a negative I. And I to the fourth is 1, so 4i over 1 is just 4i. And then 4i plus -I is 3i for the win. Done. Here we're going to distribute like so. That's I to the 7th, right? Just times 1 as itself. Plus we add the exponents. That's I to the 9th. So if you remember our chart, what we would do is we would take 7, we divide it by 4. That's 1 with a remainder of 3, which means this is like I cubed. I cubed is just negative I. I times I times I. I times I is -1 times another I is negative I. Now, when we do 9 divided by 4, we get 2 with a remainder of 1. That means I to the 9th is same as I to the 1st, which is just I. Negative I plus I is 0. Boom, done. So the first thing I'm going to do is I'm going to FOIL this top. So I've got 2 times 4, which is 8. And then 2 times -2i, that's -4i. And then I times 4 is positive 4i. And then I times -2i is -2i squared. These are going to cancel out nicely. And then -2i squared, that's -1 times -2, right? I squared is -1, so it becomes a plus 2. So then we get 8 plus 2, which is 10 on top over 1 plus I. Last but not least, we're going to multiply by the conjugate of 1 plus I, because we don't want an imaginary in the denominator, and that's 1 minus I, 1 minus I. So on top, we're going to distribute. We got 10 minus 10i. On the bottom, we have 1 times 1, which is 1. And then we have negative I and positive I, which are going to cancel out. And then we got I times negative I, which is minus I squared, which is the same as -1 or plus 1. Last but not least, we have 10 minus 10i over 1 plus 1, which is 2. And then we can divide each of these by 2, and we get 5 minus 5i for the win. Done. Here, let's go ahead and FOIL these out on top and bottom. So on top, we get 3 times 3, which is 9, plus 3i, plus 3i, plus I squared. Again, I squared is just -1, so I'm going to shortcut that, over 1 times 1, which is 1, plus 1 times 2i, which is 2i. Again, 2i times 1, which is 2i. And then we got 4i squared. But again, I squared is -1, so I'm going to skip a step and just write -4. Now I'm going to combine like terms, and I got 9 and -1 is 8 plus 6i, right? 3i plus 3i is 6i, over 1 and -4 make -3, and then 2i and 2i make 4i. Last but not least, can't have an imaginary in the denominator, so we got to multiply by that conjugate, which will be -3 minus 4i. So check this out. So on top, we're going to get 8 times -3, which is -24. 8 times -4i, which is -32i. 6i times -3, which is -18i. And then 6i times -4i is -24i squared, which again is just -24 times -1, which is +24. On the bottom, we've got -3 times -3, which is 9. Negative 3 times negative 4, which is 12i. Negative 3 times 4i, which is negative 12i. Those cancel out. So I just got to do negative 4i times 4i, which is minus 16i squared. Since I squared is negative 1, this is actually a plus 16. All right, now let's finish it off. So negative 24 and 24 cancel out. Negative 32i minus 18i is negative 50i over 9 plus 16, which is 25. Negative 50 divided by 25 is negative 2. We keep the I there. Boom, done. For 55, we again want to remove the imaginary number out of the denominator. So 4 plus I over I. We're going to multiply the top and bottom by I over I. And then for this one, we need to multiply by the conjugate of 1 minus I, which is 1 plus I. So check this out. So up top, we have 4i plus I squared, and I squared is negative 1, but we'll get to that in a second. And on the bottom, we have I squared as well. So these are both going to be minus 1 and minus 1. So that's pretty nice. So if I want to simplify this a little bit more, I can divide both by negative 1. So it's negative 4i, and then negative 1 divided by negative 1 is plus 1. Now over here, we're going to FOIL. I get 3 plus 3i minus 4i, and then minus 4i squared. And again, I squared is negative 1 times negative 4 would make that a plus 4 over, and then we got 1 times 1, which is 1. Then we got 1i, negative 1i, cancels out, and then minus I squared. And again, I squared is negative 1, so minus negative 1 is plus 1. So now this part simplifies to 3 and 4 becomes 7. 3i minus 4i is negative I over 2. And these two are being added together. So now we can simplify further. I can break this up into real and imaginary. So I've got here, let's make a little line there. I got negative 4i plus 1 plus 7 over 2, and then minus I over 2. I'll call that 1/2 I. Finally, combining like terms, 1 plus 7 halves is the same as 2 over 2 plus 7 halves, which is 9 over 2. And then negative 4i minus 1/2 I, that'd be negative 4.5 I. But I'm going to keep it as an improper, so I'll make it negative 9 over 2. 9 over 2 is the same as 4.5. Negative 9 over 2i for the win. Done. I hope you guys enjoyed this video, and if you did, please click that like button. And if you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.